In this video, I want to look at the different shapes, the repulsion of the molecules and isomers when you're looking at things like, in this case, this is ethane. You have 2 carbons, and around each carbon are the 3 hydrogens. And you can see that I can rotate, I'm spinning this long bond between the 2 carbons, and these each have a shape of tetrahedral. So you have the 3 bonds here and the 4th one is there. So when we would look at the shape of the carbon 1 bond here, this would be tetrahedral, and this carbon would also be tetrahedral. Now, one thing to be aware of is that when you have single bonds between your carbons, these molecules are free to spin, and they will spin. So what's going to happen is these hydrogens here they don't have much repulsion, but they are going to repel against each other. So they're not going to be lined up just so, they're going to be slightly opposite. So you can see that they can maximize how much distance they are between the nearest other element. So this would be ethane. Again, I have it written here. I have CH3, also known as C2H6. So this is just a single bond ethane. What I've also built is I wanted to look at double bonds. So in this one, we're going to look at, this is 2 carbon double bonded together. These are your hydrogens, and then this is your chlorines. So here is a version of C2H2Cl2. Now the chlorines are on the same side, and this shape right here would be trigonoplanar. You can see that it's flat, and because of the double bonds, they orient themselves in the maximum space. Another version, so this one has the 2 green ones on the top. Another version would be, I didn't have enough green, so I substituted orange, but it's the same molecule. You have 2 carbons, 2 hydrogens, and 2 chlorines, and a double bond. So you have these chlorine groups opposite each other. So we have 2 different ways of needing to name these. If you look at the one where they're on the same side, when items are on the same side, this is called cis. So it's the same side, it's cis. When they're opposite, this is called trans. And you can see that they are isomers. They're built with the same molecules. They just have different arrangements. Why would this be important? So if you have chlorines, they're going to repel each other with equal force, and right now they have a fair amount of space in this arrangement, but if you're looking at a bigger molecule, now this one I built is a 5 carbon chain. You can see it's 1, 2, 3, 4, 5, and I have the double bond on the 2nd carbon, so I'll go ahead and orient it this way. So 1, 2, 3, 4, 5, and my double bond is here on the 2nd carbon, and I filled all the other remaining spaces with hydrogens. And so what's happened is this has taken on a 3-dimensional shape. Now this molecule, whoops, lost the hydrogen. This molecule can spin around the axis of this single bond, and these can spin around the axis of the single bond. So they will orient themselves in a way that they are not going to be repelling as much. This would probably never happen as I have it drawn here or shown here with this molecule and this CH3 and this CH3 being so close to each other, because all these hydrogens are going to get in the way. So this one would tend to orient in a different direction so that it is not repelling from carbon 5 and carbon 1. Another thing to keep in mind is that right now this has both carbons in the cis position. Carbons 1 and carbon 4 are in the cis position. But if we were to flip it, let's see if I can get it right. If we were to flip it, now we have it in a trans position, because carbon 1 and carbon 4 are opposite in the trans position. So sometimes you're going to need to name your longer chains based on where the hydrogen and where the branch are. And if you had a drawing and it indicated that the hydrogen was on the top and the carbon group was on the bottom in a structural formula, then you could say this is trans versus the other one that we had, which was cis. So keeping in mind how you use cis and trans, this one's trans, this one's cis, and what shapes the molecules take on. They are not flat. They have three-dimensional structure, and you got to remember this one's a tetrahedral and this one is trigonal planar. Okay, so just some applications of cis and trans isomers, the repulsion of the molecules, and the space that they take on.